Okay, in this lecture we're going to continue moving through our section 2.2 material on the volumes of solids by slicing. And the next type of solid that we're going to talk about is known as a solid of revolution. So let's define first off what a solid of revolution is, and then look at our first method of determining the volume of a solid of revolution. So we would say that a solid of revolution is a solid S, which is obtained by revolving some region R in the plane about a line L, which we would call the axis of revolution. So any solid that's obtained by taking some plane region and revolving about an axis is a solid of revolution. So let us suppose that f is a continuous function such that f of x is non-negative on some interval from a to b, and let's suppose that we want to find the volume of the solid S obtained by revolving the region R under the curve y equals f of x on the interval from a to b about the x-axis. So a visual of this process is given here. Let's suppose that we have some continuous function f of x on an interval from a to b. So our graph of f of x is, since we specified it's non-negative, it lies above the x-axis. And we're looking at this solid region R that lies underneath the graph of that function between a and b. So if we're going to take that region and rotate it about the x-axis, we see that we're going to get a solid. It looks something like this, but in 3 dimensions now. So revolving that region about the x-axis, we have now a solid region shown in more detail here in this figure. And our question is, what is the volume of this solid? Now we can see here that if we were to take a plane perpendicular to the x-axis at some value x within the interval from a to b, if I slice my solid with that plane, I would get a disc shape, and if I can find the area of that disc, then I can use the method of slicing that we talked about in the first part of this section in order to find my volume. So let's think about how to find that area. So here the area of a circular disc would be given by pi times the radius of that disc squared. So here we would have pi times, now the radius of a disc is given by the value y that we move from the x-axis up to the outer edge of our solid, and this value of y is determined by the function f of x. So we see if we were to take a slice at a different value of x, I would have another disc whose radius, the distance from the x-axis to that outer edge, is given by the function f of x. So in general, r, the radius of such a disc, is given by the function f of x. So our area function, a of x, is pi times the function f of x squared. Now, another way we can sort of think about this intuitively, as we introduced in the first part of our section, if we think about taking a little representative strip through our region R of thin width dx, and I revolve that strip about the x-axis, I can see that I would have a disk, a circular disk, with some very thin width, which we would call dx, the thickness of this little cylinder. Now, the area of that cylinder we found is given by pi times f of x squared. So then the volume of this disk would be that area, pi f of x squared, times the thickness of that disk, dx. So this gives us what I would refer to as a differential of volume for our solid. I'll denote it as dV. And to get the total volume of this solid, well, I would add up the volume of each of these solids over my indicated x interval, where x ranges from a to x equals b. So this formula which we've derived gives us a theorem known as the disk method, which says the following. Let us suppose that R is the region under the curve y equals f of x on some interval from a to b. So if that plane region R is revolved around the x-axis, then the volume of the resulting solid of revolution would be given by v, and it's found by integrating from a to b the function pi times r squared, where our radius was given by the function f of x with respect to x. And that pi, I can of course pull out in front of my integral. I can pull any constant that I want out in front of my definite integral. So this is referred to as the disk method. It's a special case of the method of slicing where our cross sections perpendicular to an axis are circular disks. So let's look at some examples making use of this disk method. In our first problem, we're asked to find the volume of the solid obtained by revolving the region bounded by y equals the square root of x, y equals 0, which is the x-axis, and x equals 4 about the x-axis. So as we did with the method of slicing, it typically helps to visualize our region here. So let's start by sketching this. So we're looking at the region in the plane bounded by y equals the square root of x, which looks something like this. The line y equals 0, which is our x-axis that we've already shown. And the line x equals 4, which would be a vertical line passing through x equals 4. So our corresponding y value here would be 2, or square root of 4. And then we see that square root curve and our x-axis intersected at 0. So our region of interest here is the following region, and we're going to take this region and revolve it about the x-axis. So we get a solid, and the question is, what is the volume of that solid? So to do this, let's think about sketching in a little representative slice or cross-section of my solid at a point x within my interval of thin width dx. And we see that if we were to revolve that slice around the x-axis, I would have a disk. Now the radius of that disk is given by the distance from the x-axis up to my curve, which was the curve y equals the square root of x. So here the radius of the disk I get, if we think about revolving that strip about the x-axis, we get this disk. And the radius of that disk would be the distance from the x-axis up to that outer edge, which is given by our function root x. So here, I'll say by using the disk method, the volume of our solid is found by integrating pi times f of x, which was root x squared, with respect to x, over whatever x interval specifies our region. And we can see from our sketch here that the lower bound on x was 0, and then we can range up to the other edge of our solid, which was corresponding to x equals 4. So we're integrating from 0 to 4 here. So in this example, not too difficult, we have pi times the integral from 0 to 4, and the square root of x squared would simply be x dx. So for our antiderivative, we have pi, and then the antiderivative of x to the first would be 1/2 x squared. So we have pi over 2 x squared, which we're evaluating from 0 to 4. So we have our constant pi over 2 out in front. When we evaluate x squared at 4, we have 16, and then we subtract the value that we get when we evaluate at x equals 0, which would be 0. So we've got pi over 2 times 16, which leaves us with 8 pi for the volume of the solid which is being described here. Okay. So let's look at another one. In this next example, we are asked for the volume of the solid obtained by revolving the region bounded by y equals 1 minus x, y equals 0, which is the x-axis, and x equals 0, which is the y-axis, about the x-axis. So here let's try to sketch the region first. So we're looking at the region bounded by y equals 0, which is my x-axis, x equals 0, which is the y-axis, and the line y equals 1 minus x, which is the line whose y-intercept would be 1, and it has a slope of -1. So its x-intercept is also 1. So the region of interest is this triangular region shown here. And we're supposed to take that region and then revolve around the x-axis. So let's think about how we would do that. If we think about taking a little representative slice through our region at a point x of thin width dx, if we revolve that slice around the x-axis, we can see that we would get a disk shape of thickness dx. And so the area of that disk would be pi times the radius squared, where the radius of our disk is the distance from the center, or the x-axis, up to the outer edge, which is given by this curve, y equals 1 minus x. So of course, depending on what value I choose for x, I'm going to have a larger radius for my disk, but the radius is always given by 1 minus x. So we see, since we have a disk shape for our cross-section, that we could use the disk method. So here I'll say using the disk method. The volume of our solid is found by integrating pi r squared, where the radius of our disk is given by the function 1 minus x. So we've got 1 minus x squared with respect to x, over the x interval, in this case from 0 to 1. So we can see that one edge of our solid corresponds to x equals 0, and then we can take slices up until we hit x equals 1. So to evaluate this, well, there's a couple of approaches we could use. We could expand 1 minus x squared and then integrate term by term. Alternatively, we could make use of a u substitution. Either approach works here. So my own preference, I might expand this first. So I have pi times the integral from 0 to 1 of 1 minus 2x plus x squared dx. So for our antiderivative, we would have pi times x minus x squared plus 1/3 x cubed, and we're evaluating from 0 to 1. So when we substitute x equal 1 in for x in this antiderivative, we have pi times 1 minus 1 plus 1/3. And then we subtract what we get when we evaluate at x equals 0, which would be 0 here. So we can see, of course, our 1 and negative 1 cancel. We're left with pi times 1/3, or pi over 3, for the volume of the solid described here. Okay. So let's take a look at another one. In this next example, we're asked for the volume of a solid obtained by revolving the region bounded by y equals natural log of x, x equals 0, which is the y-axis, y equals 0, which is the x-axis, and the horizontal line y equals 2, all about the y-axis. So let's take a look at this one. Start by sketching our region, which was bounded by the x and y axes, along with the curve y equals the natural log of x. So we know that when x is 1, the natural log of 1 is 0. So our curve looks something like this. And then it's also being bounded by, we were told, the line y equals 2. So that is a horizontal line passing through y equals 2. So our region of interest is this shaded region bounded by those values. And we're told that we're going to revolve this region in this problem about the y-axis. So let's think about how we could use the disk method in order to calculate that volume. So here, since I'm revolving about the y-axis instead of the x-axis, it might be beneficial to think about a representative slice through my region, which is perpendicular to the y-axis instead of the x-axis. So in our earlier examples, when we were revolving about the x-axis, we used a little vertical strip. So here, since we're revolving about the y-axis, let's try a little horizontal strip taken at a value y, units above the x-axis, somewhere between 0 and 2. And let's call the thickness of that strip dy, or a differential of y. So we can see that if we revolve that strip about the y-axis, we're going to get a disk of a thin thickness, dy, and the radius of this disk, the distance from the center out, will be the distance from our axis of revolution out to the edge, which is defined by this curve, y equals the natural log of x. So let's see if we can use the disk method here. So I'll say using the disk method, the volume of this solid would be found by integrating pi times the radius of our disk squared. Now what's a little tricky here, our radius, r, in this disk, is going to be the horizontal distance from the y-axis out to our curve. Now that horizontal distance that we travel is what we call x. But my equation for this boundary curve, that is the distance I'm allowed to move outward, is given as a function, y as a function of x. So if I solve this equation for x by exponentiating both sides, I would have x is e to the y power. So the radius of my disk here, which is the horizontal distance I travel from the y-axis, is given by e to the y. We see depending on what value of y I choose, I can travel a further distance, so I'm going to have a larger radius depending on what I choose for y. So here we would be integrating our radius, which is e to the y squared, and the thickness of our slice was dy, and we're integrating or adding up the volumes of these little disk slices over the y interval from y equals 0, or the x-axis, up to this horizontal line y equals 2. So before I integrate, I'm going to simplify the integrand a bit. I've got pi times the integral from 0 to 2, and e to the y squared is e to the 2y. We're integrating with respect to y. So our antiderivative here would be our constant pi, and the antiderivative of e to the 2y is half of e to the 2y. So I have pi over 2 e to the 2y, which I'm evaluating from 0 to 2. So I have out in front my constant pi over 2, and when I evaluate this antiderivative at y equals 2, I have e to the 4th power, and then I subtract e to the 0 power, which is 1. So this expression would be the volume of the solid obtained by revolving that region about this y-axis. Okay. So there are some cases where the axis of revolution may not always be the x or the y-axis. In general, we could think about revolving a plane region about some other vertical or horizontal line in the plane, and we could ask ourselves what the volume of the resulting solid of revolution would be. So in that case, where our axis of revolution is not one of the x or y axes, our formulas for the disk method get a little bit trickier. In particular, determining the radius of our disk is a little bit more difficult. So let's consider some examples of this. In our next problem, we're asked to find the volume of the solid obtained by revolving the region bounded by the square root of x, y equals 0, or the x-axis, and x equals 4 about the line x equals 4. So here, this is similar to a problem that we had looked at a bit earlier in this lecture, where within the xy plane, our region of interest is the region bounded by the curve y equals the square root of x, which is shown here. The x-axis, so those curves intersect at x equals 0, and the line x equals 4, which would be the vertical line passing through 4. So we're looking at this shaded region. And in our earlier example, we were revolving this about the x-axis, In this problem, we are interested in revolving about the line x equals 4. So let me draw in the line x equals 4. So that is this vertical line passing through x equals 4. And this is our axis of revolution. We're going to be revolving about that axis. So let's think about how to do this. So when we revolve this region about the vertical line x equals 4, if we want to make use of the disk method, so if we want our cross sections of this solid to be disks, we would need to take a slice which is perpendicular to my axis of revolution. So since I had a vertical axis, I would take a horizontal slice at a height of y units above the x-axis and of a thin width dy. So I can see, of course, if I revolve that slice about the line x equals 4, I'm going to get a disk of a thin thickness dy. And the radius of this disk is going to be the distance from the center of my disk, so the axis of revolution, out to the edge of my region, which is defined by this boundary curve, y equals the square root of x. So let's think about how to find that distance traveled here. So here we would have our radius r of this disk determined in the following way. So we know that the total distance from the y-axis, let me maybe use a different color. So the distance from the y-axis to the vertical line x equals 4 is 4 units. And from that value, to get my radius, I want to subtract the distance that I'm moving from the y-axis out to my curve. So that horizontal distance that I'm moving from the y-axis outward to the edge of my curve is what we call x. And here that distance is defined by this curve, y equals the square root of x. So if we solve this equation for x, we would have x is equal to y squared. So the radius r of my disk here is found by taking the total distance from the y-axis to my axis of revolution, which was 4 units, we said. And then I subtract the distance that I traveled from the y-axis outward to my curve, which is given by x, where x is equal to y squared. Depending on where I choose my value y, of course I have a larger radius or a smaller radius for this disk. So once I know the area of my circular disk, I'm ready to use the disk method to find my volume. So our volume is found by integrating pi times the radius squared. Now here, the radius of our disk was given by 4 minus y squared. We're integrating with respect to y, since we were taking little horizontal slices of thin width dy. And let's think about the limits of integration here. So our lower boundary for y was the x-axis, or y equals 0, and we can take points up until this value for y. Now, how do we find this y value? Well, this value corresponds to the square root of 4. So our x value on that edge was 4, so y, being the square root of x, would be 2 at that edge. So we're going to integrate from 0 to 2. So let's see what we have. We have pi times, and we're squaring this quantity, radius squared, 4 minus y squared squared. We have pi times the integral from 0 to 2 of, when we expand 4 minus y squared squared, we get 16 minus 8y squared plus y to the 4th dy. And taking the antiderivative of this function, we have pi times 16y minus 8/3 y cubed plus 1/5 y to the 5th, evaluating from 0 to 2. So let's see what we're left with. We have pi times, when we evaluate this antiderivative at y equals 2, we get 32 minus 8/3 times 2 cubed would give us 64/3 plus 2 to the 5th, which is 32 times 1/5 is 32/5. And then we subtract what we get when we evaluate at y equals 0, which would be 0 here. So in order to simplify this, if I'm a little bit clever, I can see that each of these terms I could factor out a 32 from. So I would have a 32 pi. And then after I factor out that 32, that would leave me with a 1 minus 2/3 plus 1/5. So that gives me a 32 pi. And then let's see, my 1 minus 2/3 would be 1/3 plus 1/5. So that gives me 32 pi. 1/3 plus 1/5 would be 8/15. And then my 8 times 32 pi gives me a 256 pi over that denominator 15. Okay. So we see in this example that if the axis of revolution is not the x or the y axis, determining the radius of our disk becomes a little bit trickier. So let's look at another example of this. So in this next one, we're asked for the volume of the solid obtained by revolving the region bounded by y equals x squared and y equals 1 about the line y equals 1. So sketching our region, we're looking at the region bounded by y equals x squared, which is a parabola opening upward, and the line y equals 1, so that is a horizontal line passing through 1. So where y equals x squared would intercept, y equals 1 would be at the x values, x equals -1 or +1. And we're supposed to take this region bounded by those curves and revolve about the line y equals 1. So our axis of revolution is going to be this line which defines the upper edge of our region. So if I want to make use of the disk method in order to find this volume, since I'm revolving around a horizontal line, in order to get a disk shape, when I revolve around a horizontal line, I would have to take a little vertical slice through my region of some width dx at a value x, somewhere between -1 and +1. So let's see what we have here. When I revolve this slice, this representative strip, about the line y equals 1, well, I can see that I get a circular disk shape, so I'm going to be able to use my disk method, where the thickness of this is dx, and the radius of my disk is going to be the distance that I move from the center of my disk, which would be the axis of revolution, outward to this curve, which is defined by y equals x squared. So let's think about how I'm going to find that radius. So I know that the total distance from the x-axis, let me maybe change colors here, from the x-axis up to my axis of revolution is 1 unit. And the value that, or the distance I travel from the x-axis to this edge is given by the equation y equals x squared. So the radius then of my disk is found by taking the total distance from the x-axis to the axis of revolution, which was 1, and I'm subtracting the distance from the x-axis to my curve, which we just said is x squared. So, using the disk method, our volume of this solid of revolution is found by taking pi times the integral over our x interval. And we can see here that our x interval ranges from x equals -1 up to x equals +1. And we're taking our radius, which was 1 minus x squared, and squaring it. Here we're integrating with respect to x, since we were looking at thin slices of width dx. So let's see what we have here. So we can proceed by expanding this expression and evaluating at the endpoints. And one thing I'll mention in this example that we could use to make our work a little bit easier is the symmetry of this region. So in particular, if I were to calculate the volume of this solid by integrating from x equals 0 to 1, so that is if I took this shaded region and revolved about the line y equals 1 and got my volume, well, I could then just double that value to get the volume of the solid I would obtain by revolving this entire region about the line y equals 1. So let me say by symmetry, our volume V could be found by taking twice our pi and then just integrating from 0 to 1 instead of from -1 to 1. The function 1 minus x squared with respect to x. So let's see what we have. We've got a 2 pi times the integral from 0 to 1 of, if we expand 1 minus x squared, we have 1 minus 2x squared plus x to the 4th dx. So we now have a 2 pi times the antiderivative of this function would be x minus 2/3 x cubed plus 1/5 x to the 5th from 0 to 1. So that gives us a 2 pi times, when we evaluate at x equals 1, we have 1 minus 2/3 plus 1/5. and then we subtract what we get when we evaluate at 0, which would be 0. And so we're left with 2 times 1/3 plus 1/5. So we have our 2 pi times 1/3 plus 1/5, which we had found in the previous example was 8/15. So multiplying by 2 pi, we get 16 pi over 15 for the volume of this solid. So again, these last two examples are illustrating if our axis of revolution is not simply the x or the y axis, making use of the disk method is a little bit trickier because we have to be a little bit careful about finding an expression for the radius of our disk.